Imagine the air around us, abuzz with invisible signals. These signals carry information, connecting our world in countless ways. But how do we make sense of this invisible symphony? The answer lies in understanding a fundamental concept: frequency. Frequency is the heartbeat of a signal. It tells us how many times a wave repeats itself in a given time. Think of it as the tempo of a song. A fast tempo means a high frequency, a slow tempo means a low frequency. Just like each musical note has a unique frequency, so does every signal that travels through the air. Understanding frequency is key to unlocking the secrets of these invisible messengers. It allows us to design antennas that can effectively transmit and receive information across vast distances. Without a grasp of frequency, we would be lost in a sea of static, unable to decipher the symphony of signals around us. For centuries, scientists grappled with the complexity of signals. How could we possibly understand the intricate dance of waves that carried information? The answer came in the form of a groundbreaking mathematical tool: Fourier analysis. This elegant theory, developed by the French mathematician Joseph Fourier, provided a revolutionary way to understand complex signals. It revealed that any periodic wave, no matter how complicated, could be broken down into a sum of simple sine waves. This was a profound discovery, akin to finding the fundamental building blocks of the universe of waves. Fourier analysis gave us the key to unlock the secrets hidden within seemingly chaotic signals. It allowed us to dissect any wave, no matter how complex, into its fundamental sinusoidal components. Imagine a complex waveform, its peaks and valleys tracing an erratic path across our screen. This might represent a radio signal, a sound wave, or even a beam of light. Fourier analysis allows us to deconstruct this intricate dance into its basic steps. We begin by identifying the simplest sine wave that contributes to our complex signal. This wave, called the fundamental frequency, sets the basic rhythm. Next, we add more sine waves, each with a higher frequency and a specific amplitude. These are the harmonics, adding their unique flair to the overall dance. As we layer these simple sine waves together, something amazing happens. The sum of these individual components begins to resemble the original complex wave. Step by step, we reconstruct the signal, piece by piece. Section 4. Rebuilding the symphony from sinusoids to signal. With each added sine wave, our reconstruction becomes more accurate. The peaks and valleys align, and the intricate details of the original signal begin to emerge. It's like adding instruments to an orchestra, each playing its part to create a harmonious whole. What began as a chaotic jumble of waves transforms into a well-defined pattern. The seemingly random fluctuations now make sense, each a result of the interplay between the simple sine waves. We have taken the complex and broken it down into the simple, revealing the elegant mathematics that govern the world of waves. This process is not just a mathematical curiosity. It has profound implications for how we understand and manipulate signals in the real world. Section 5. A universe of waves, from radio to light. The beauty of Fourier analysis lies in its universality. It's not limited to just sound waves or radio signals. This powerful tool can be applied to any type of wave phenomenon, from the gentle ripples in a pond to the light that illuminates our world. Think of the vibrant colors we see around us. Each hue represents a different frequency of light. Fourier analysis tells us that these colors, when combined, create the white light we perceive from the sun. The same principle applies to the radio waves that carry our favorite songs, the television signals that bring us entertainment, and even the microwaves we use to heat our food. All these signals, despite their apparent differences, are governed by the same fundamental laws of waves and frequencies. Section 6. Antennas and the dance of frequencies. Now let's bring this back to antennas. These ingenious devices are designed to interact with specific frequencies of electromagnetic waves. Remember, each frequency corresponds to a particular wavelength. An antenna's size and shape are carefully chosen to resonate with the desired frequency. Think of it like a tuning fork. Just as a tuning fork vibrates at a specific frequency, an antenna is designed to efficiently transmit and receive signals at a particular frequency. When a radio wave, carrying information at its specific frequency, encounters an antenna tuned to that same frequency, something wonderful happens. The antenna resonates, capturing the energy from the wave and converting it into an electrical signal that our devices can understand. Section 7. Organizing the spectrum, a glimpse into frequency bands. With countless applications using electromagnetic waves for communication, navigation, and more, it's crucial to avoid a chaotic clash of signals. Imagine if every radio station, TV channel, and cell phone operated on the same frequency. It would be impossible to distinguish one signal from another. To maintain order in the airwaves, we divide the electromagnetic spectrum into specific frequency bands. Each band is allocated for a particular use, ensuring that different technologies can coexist without interference. This organized allocation of the spectrum is essential for the smooth functioning of our increasingly interconnected world. But what are these frequency bands, and how do they shape the technologies we rely on every day? That's a story for our next exploration into the fascinating world of antenna design and the electromagnetic spectrum.